Hello everyone and welcome back to your YouTube channel and welcome to this amazing series of video. As you must be aware, we are recording this series of video practical examples and theory related to electromechanical conversion systems. And when we are dealing with electrical machines, specifically rotating electrical machines, a very important subject is the force, the torque that is created in those components. And also, if we are talking about AC generators, we need to think about the induced EMF. Those concepts are extremely connected to electrical machines, but also is very important when you are working with transmission lines or transformers and many other of the important power system devices. So today we have a very exciting, a very different numerical example for all of you. And here, let me start by reading this statement over here. A coil of a moving coil instrument is wound with 42.5 turns. Wow, this will be blowing your head. 42.5 turns. Well, don't be scared. If you go here to the figure, you can see the details of the coil. What is important that you understand is that basically we have a coil. You can see that this is a rectangular coil, that there is a current moving around and then the current is leaving the coil. But what is important is that these 42.5 turns mean that the side A, you can see over here 43 wires, and in the area B, the side B that is below, you can see 42. So 42 plus 43 divided by 2, that is 42.5. So don't be scared. When you see this decimal point over here defining 42.5, what you need to understand is that there are more copper, more wires on the top and less here at the bottom, okay? The mean width of the coil is 25 millimeter and the axial length of the magnetic field is 42 millimeter. If the flux density in the air gap is 0.1 Tesla, in other words, B equals 0.1 Tesla, now the question is calculate the total torque on the coil when it's carrying 50 milliamps. In other words, what we want to obtain is the torque that is developed by this beautiful rectangular coil. And the calculation is extremely simple. Because the first step, my dear students, is that we need to create a graphical representation to understand the situation over here. You can see here at the top, the side A, the side B. And what is important that you understand is that we have in blue this magnetic flux density of 0.1 Tesla. The current moving on the top is going to the right. I mean, it's moving across these 43 wires. And below on the side B, we have the same current and is interacting with the magnetic flux density over here. So we have here FA, that is the force created by those 43 wires. And we have force B, created by the 42 wires. In other words, what we want to do is we have the force A here at the top created by 43 wires, and at the bottom we have the force B created by 42. So here the length is 20 millimeters and over here you can see that is 25. And the half, it will be 25 millimeter divided by 2, that is 12.5 millimeters. So in order to calculate the torque that we will obtain here, we need to calculate the individual forces A and B. And that is the next step. So to calculate the forces A and B, it's very, very simple, okay? Because we will use this equation that we already know from the previous videos, but also I spent a lot of time telling you this equation on the theory. The magnitude of the force is numerical equal to N, that represents the number of turns, I, that is the intensity of the current, L, that is the length, and B, that is the magnetic flux density. So now, what I will do is calculate the total force on the section A. So this force is the number of turns on A. You can see over here the 43 wires. You can see 0.1 Tesla. This is the conversion of 20 millimeter, because remember B is 20 millimeter. And if we convert into meters, it means 0.02 meters, okay? And finally, we have here the current, and the current is basically 50 milliamps. Remember, the current is 15 milliamps. That is equivalent to 15 exponent minus 3 amps, or in other words, 0.15. So when we put the number together in the calculator, we obtain this force over here, and this force over here is 0.00129 newtons. Now we can do the same for the section B, and in this case, the total electromagnetic force will be the 42 wires, because remember, this is the NB, 42 wires. And now we substitute B, L, and I, and we obtain the force on the section B. What is important is that you can see that the force A is larger than the force B, and the reason is that there are different number of wires on the side A versus side B. So that is very important to keep in mind. But now what is important that you understand is that those forces, let me do something here. Those forces over here, remember we have here the coil, and we have those forces. This is the force A, and this is the force B. And those forces, they are at a distance, let's say this distance is R, and those forces are creating this torque over here, yeah? So what you need to understand is that the force A creates a torque that is force A multiplied by R, and the force B is creating another torque, and the total torque here will be the torque A plus the torque B. In other words, what I am telling you is that FA plus FB multiplied by R, this is the total force in the coil multiplied by R, that will be the total torque. In other words, both forces are pushing on the same direction. Both forces are using the same distance to the rotating point. So the torque A plus the torque B is equal to the total torque. And using those equations by basic mathematics, we can sum those forces and we obtain the total force. And the total torque will be the total force multiplied by the distance. So that is what I will do right now. What I will do now is basically we can calculate the total force, the total electromagnetic force. That will be force on the side A plus the side B. You have the numerical value over here, 0.00129 plus 0.00126. and we obtain here a equivalent total force. So the total torque T will be the total force multiplying by the distance creating the torque. In this case, remember, is R that we already show is 0.0125 meters. So the numerical result is here. The total torque that you will have in your coil is basically this number over here, 31.8 exponent minus 6 Newton per meter, or in other words, 31.8 micronewton meters. So this is the answer. This is the answer for this example. And I hope the explanation is useful for you, and I will see you at the next video. Bye now.